Guys. Just gonna send this link to one of my fellow SI leaders. Alrighty. I'm gonna turn this overhead light on here, just to make sure I got that good lighting for the video. And we are gonna prep you guys for test 3. So the first thing I'm gonna do is I'm actually gonna give you guys a resource. So open your phone right now and go to the group chat, because I'm gonna give you a reference point. Please use this along today's video. So I just sent something to the group chat. It is a photo, and this is how it's basically the most cut and dry instructions you will find out there for how to determine intervals of increase, decrease, and classify the local extrema. And this goes, it's very detailed, which is why I wanted to share it with y'all. It goes into it explains critical numbers. It says it tells you to divide the domain. I mean, it's step by step, it's numbered. It's really useful. I use it a lot in Calc 1. So determine the signs. Yep. Apply increasing / decreasing test. Yep. So it has all the little fine print details that you'll need to do very well with this stuff. And then classify local extrema. Yep, so second test, second derivative test, first derivative test. It has all the criteria for each test. So this should be helpful for today's session. We're kind of just going to be looking around at the concavity, optimization, some integration, and perhaps a few Riemann sums as well. So, let's do a test for concavity to start today off. Okay, so our first problem is going to be f of x. Ooh, that's depressing. You guys said green, you can't see. F of x is equal to x cubed minus 6x squared plus 9x plus 30. So the theorem for the test for concavity states that f is a continuous function on the closed interval from a to b. Suppose f prime and f double prime exist on the open interval a to b. The minimum is if f double prime of x is greater than 0 on AB, then f is up on AB. Maximum if f double prime of x is less than 0 on AB, then f is down on AB. So that right there is the second derivative test. So let's take the first derivative to start this problem off. So we got f prime of x equals, and this is just power rule, 3x squared minus 12x plus 9. And of course, this is a constant, and the derivative of a constant is always 0. So now what we're going to want to do, well, I would say we should factor it first, because this looks kind of like it's going to work out here. So let's divide 3 out of everything. So x squared minus 4x plus 3. So then f prime of x is equal to 3 times x, add that, multiply that, so minus 3 minus 1. Yeah, see, you learn a few tricks there. I'll give you a hint on how I factor that so quick. So I'm sure a lot of you already know this because I know quite a few of you probably are getting pretty frosty with your algebra by this point in the class. But for when you're factoring like a 3-term expression like that, if you've got a negative sign in the middle and a positive sign at the end, well, that could only mean that both of these are going to be negative signs. And hear me out, because you can, you have to multiply this and this to get this, and you have to add this and this to get that. So the only way we can have a negative term in the middle by adding 2 negative terms, and have a positive term there means that both terms must be negative. And that's because a negative times a negative is positive. So just a quick little trick there. All right, so now let's see. Oh, so you know what, guys? We are going to use the first derivative test for this one because it's so nicely laid out for us. So this is going to give us x equals 3 and x equals 1. I'm just going to write the second derivative too. F double prime of x is equal to 6x minus 12. Factors out to 6 times x minus 2. Okay, so we know that this is a polynomial expression. So the way we're going to write this, it's like this. So we go, our domain is going to be negative infinity, and this is our domain for f prime of x. Negative infinity, 1 to 3, union 3 to infinity. So now what we're going to want to do here is we're going to want to draw it. So we're starting negative here, right? But as that's going up, we're reaching this 1. You know what? Let's graph it. So x, y. Let's just start with 0 for x. So it's going to give us 30. 1. It's going to give us 1 minus 6 plus 9 is 5 plus 9, or negative 5 plus 9, which is going to give us 4 plus 30 is 34. Then we'll do graph here for f prime of x, which is equal to 3x squared. So let's do 0. That's going to give us 9. And let's do 1. 3 times 1 is 3, minus 12 is negative 9, plus 9 is 0. Oh, it's kind of neat. So now let's graph these two. So x at 0 is going to be y at 30. 1 is 34. 0, 9, and 1, 0. So what I'm going to do, guys, is get my graphing calculator real quick, just so I don't have to spend this entire session drawing this graph. But what you're going to see here, and I'll show this, I'll draw it out right after I graph it on this as well, because I know that we have a good bit of time here, but I don't want to stay stuck on one problem for too long, because I'll force myself to solve it. So I'm going to give us a little bit of help here. Oh, it means it's an increase. Okay, so this is actually pretty cool, y'all. This is pretty cool right here. So it ends up as a parabola for the graph of this first derivative, and then the second derivative is a large, very large cubic function. Let's see if I can draw this right. So something like that, where they're intersecting right here. And the reason I'm kind of drawing this out, guys, is because this is going to help you think about this in a different way. What's up, Hayden? So the reason this is going to make you think about it in a different way is because if you guys remember the basic functions of this class, right? So let's say we got f of x equals x cubed, f of x equals x squared. So a cubic function looks something like that, right? I'm not the best artist here. This one looks like that. And then if we had f of x equals x, it would look like that. So the reason this is important is because this right here is telling us what's happening with this problem. And I'm sure that that drawing probably doesn't make a whole lot of sense, but it's about to. Because think about it in higher dimensions. So in differential equations, the degree of the problem is the highest exponent power of the variable, which means that, you know, Professor Kang has surely spoken of this because he's a linear algebra professor as well. I know that because I took his class. Made an A, by the way, just in case anyone's curious. But in linear algebra, you know, you're limited to realms of numbers. Not realm isn't the right word, but that's just, you're limited to degrees. 3, 2, 1, like you can have 2s and 3s, but you can't have 4s and 3s because you have 4 dimensions in three-dimensional space. And the same is happening right here with this math. This is just us finding a way to look at the lower dimensions of the problem by deriving it, so we can understand the shape of the higher dimensions. So for instance, if the second derivative is upward facing, which is positive, let's look at that handout I sent all of y'all. So for each critical number C, let's look at the first derivative test. So if f prime changes from negative to positive at C, then C is a local minimum. If f prime changes from positive to negative at C, then f of C is a local maximum. If f prime does not change sign at C, then f of C is neither a local maximum nor a local minimum. And remember, the way we find critical numbers is f prime of whatever critical number C it is must be equal to 0. That is the definition of critical numbers. And that is why over here we selected x equals 3 and x equals 1 as our critical numbers. I am going to be right back, y'all. My throat is awfully dry, so I'm going to get water and a different colored marker because I don't know, writing in black and red just kind of stresses me out. You know, I always feel like I'm making a mistake when I'm writing in red. It's obviously not logical, but I don't know. Those purple markers, they just hit different. These ones right here. I'm gonna fill my water and then we're gonna finish solving this problem. Also, congratulations to everyone attending this video. I know that it has not been an easy summer by any means, but the fact that you have made it this far, I'm assuming means that you at least have a chance at passing the class. And I would like to be the first to say, good job, you guys all worked hard, but now is not the time for congratulations quite yet. So I just wanted to let you guys know that even if you don't pass this class, it is a very difficult class and you should be proud that you've made it this far at least. This class has a very high fail rate, so if you are in a position where you're going to end up failing the class, you shouldn't feel horrible. I mean, Calc 1 was the only B I ever made, and I made an 89.4 or something. But that's the only B in a math class I kind of saw I've ever made, and it was just because, I don't know, I was being lazy that semester, I guess, but I swore vengeance on math I kind of saw to never get a B in a math class again, and I have not done so yet. I have not made one since. So where was I? Critical numbers. F prime of C equals 0, so we've got the critical number C equals 3, and the critical number C equals 1. So now let's look at the first derivative test again. If f prime changes from negative to positive at C, then f of C is a local minimum. Changes from negative to positive at C. Okay, so let's see what happens. So this would be f prime x is right here. So let's plug in 1 for this one. So no, hold on. Let's see, so let's plug in C for f of x. So we go 1 minus 6 plus 9 plus 30. It's going to give us negative 5, 39, 34. And then 3 at that is going to be a C. 3 to the third minus 6 times 3 to the second plus 9 times 3 plus 30 equals 30. So then when x equals 1, we get equals 34. When x equals 3, it equals 30. So then parabola. It's going to be concave up, because this is just positive. I mean, I'm trying to find a way to make this sound more complicated than it needs to be, but like, if you guys just look at the shapes of the graphs, most of these should be pretty easy. So the idea of all of this, essentially the main idea, the backing for this, is that we're focusing around a critical number where f prime of x equals 0. That means that the slope is not changing at that point. So that means that we're going to have a tangent line there. First derivative test, f of c equals local maximum. If f prime of, there it is, geez. If f prime of x is greater than 0 for a is less than x is less than c, and f prime of x is less than 0 for c is less than x is less than b, then f of c equals the local max. So, geez. Okay, so here's how we're going to do this. So our first thing is going to be 30. 34. So 34 is greater than f of 0. 30 is not greater than f of 0. And this right here is f of 1, or x equals 3 for 30, and x equals 1 for 34. So what that means is that the critical value for the second derivative is greater than the critical number for the first derivative. Is greater than the value of f at 0 than the first derivative. That's essentially what this test is saying. It says, this is for the theorem for concavity. If f double prime of x, wait, wrong page. First derivative test is what I meant to say. So if f prime of x is greater than 0, then f at 0 for a is less than x is less than c, and f prime of x is less than 0 for c is less than x is less than b, then f of c is the local max. Inversely, the opposite situation would be f of c is the local minimum. If f prime of x has same sign on both sides of c, then f of c is not max or min. So in this situation, our minimum value is going to be at x equals 3. And the reason for that actually is over here. And I'm sorry if I'm over-explaining some of this, y'all. I just really want to tackle this fully. Where did my eraser go? Oh, the cat moved it. So negative, positive. Okay. And the reason this works right here, the final big reveal, tangent lines. So remember I was talking about the level of degrees, right? So this is the critical values domain. This is the domain with the critical numbers for f prime of x. And if you look, the critical numbers are all at tangent lines, which is why it allows us to understand that. So then it says, if f of x is increasing after that tangent line, then that point is, if it's increasing on this side and decreasing on this side, then this point is a minimum. So this is kind of harder to see with this one because it's a cubic function, but we're going that way. So this is a local minimum at x equals 3. And this is a local maximum at x equals 1. So that was probably a little tricky to follow, so I'm going to go over a few things real quick. Like the first thing I did was I took the first derivative, I took the second derivative, and the reason I did that is just because I'm going to see if the second derivative test is faster or not. I'm just taking one problem and working through all the concepts, and then we're going to start looking at some individual cases for each concept. So this is just kind of me grabbing the bull by the horns so I can show you guys, like, this is how you gotta, this is me without looking at the material. Then I'm gonna bring in my little cheat sheet that I made for myself so we can go through individual concepts. Because I wanted you guys to see me just, kind of face this head on so you guys know what you need to be thinking when you haven't seen a problem like this. Because I haven't worked these types of problems in a while, but I was like, okay, I know how to find minimums, maximums. I know that these graph shapes are gonna be changing, et cetera, et cetera. I know that each derivative is gonna lower it down a degree of the graph, which is essentially all deriving a graph is. If you think about it graphically, it's lowering the degree of the formula, of the function, which puts it 1 degree lower, 1 degree lower, and then it's similar to dimensions, but not quite. Not quite, but what I thought about was a derivative is just taking a cubic function and turning it into a parabolic function, or taking a parabola and turning it into a linear function, et cetera, et cetera. So I didn't think about this as a big, long process of finding critical numbers and optimizing. I thought of it as, well, here's this graph. Let's find a way that we can work through it without having to overcomplicate it, which some of you are probably laughing right now because I probably definitely did overcomplicate it a little bit, but let's look at the second derivative test now. So we've got f double prime of x is equal to 6x minus 12. So where f, let's see what that test is. Let's reference that sheet I sent out to the group chat. So f double prime of c is greater than 0, and f of c is a local maximum. F double prime of c. Okay, so this is actually probably a much more convenient way to take this, because now we've already got the numbers right there, right? So let's test it again with the double derivative, with the second derivative. So we got f double prime of 1 is equal to 6 minus 12, which is negative 6. Oh my gosh, this is so much nicer. And then f double prime of 3 is equal to 18 minus 12, so it's positive 6. So now let's see. F double prime of c is greater than 0, and it is a local minimum, cha-ching, because 6 is greater than 0. If it is less than 0, then it is a local maximum. Yeah, pretty cool, right? And then here's the kicker, though, with the second derivative test. So I just made you guys do all that big brain thinking and stuff, right, with the first derivative test, because that's a real pain in the butt sometimes, but I wanted you guys to all see the big picture there. So Now we got the second derivative test, and the reason I showed that to you after the first derivative test is because I think the second derivative test is much more efficient, but it doesn't always work, because if f double prime of c equals 0, then the second derivative test is inconclusive, and you have to use the first derivative test. So this is just kind of a general walkthrough of what types of problems you'll be seeing with critical numbers, all that stuff. So our next thing is probably going to be, let's think. I'm thinking some L'Hopital, I'm thinking some rolls, concavity, f double prime of x on AB, then f is up on A. I'm pretty sure that's supposed to say C. That's my bad. Alrighty. Rolls theorem. Let's do some rolling theorems, some Rolls theorem, because now we know stuff. See that? I'm teaching it to you guys backwards because you already learned it forwards. So if I teach it to you forwards again, it won't make any sense. Well, I'm sure it would, but what fun is that? That's right. I'm starting backwards, and then I'm going to finish with the integral just to keep you guys paying attention. Because you know what? If there's one thing I've learned about math, it's that the problem you don't want to do is the one you're going to end up seeing on the test. That's always how it is. And it isn't because the teacher's evil, guys. It's because that's part of the curriculum, and you already knew it was part of the curriculum, but you chose not to learn it instead. Or I don't know, maybe you had a really hard time, but if that's the case, then welcome, because I'm here to make it an easier time. Oh man. See, Haley just goes to work and I do my little math videos. That's kind of fun. Alrighty. Rolls theorem, here we go. Yes. I'm excited. We're doing math. This is cool stuff, by the way. If you don't think this is cool, then I don't think past tests have been kind of whack. Yeah, they sure have. I mean, I haven't taken them personally, but I'm assuming you wouldn't lie to me. But that's okay. We're going to make this test less whack, because we are going to be detailed with our approach. So let's start with a problem, and then as we work the problem, I'm going to explain the theorem, because I am no pure mathematician, so I like to learn as I go. I thought I wanted to be a pure mathematician for a while, but wasn't really about it. So this is the problem. Let's see what Rolls says about it. F is a function defined on a closed interval AB. If f is continuous on AB, f is differentiable on AB, and f of A equals f of B. All these are true, then at least one number C in the open interval AB for which f prime of C equals 0. In the open, if all these are true, there is at least one number C in open interval A to B for which f prime of C equals 0. Okay, well, let's test some of these things. So x squared minus 5x plus 6, that looks like a polynomial expression to me. So it most definitely is continuous. Continuous, check. All real numbers because it's a parabola. So differentiable on AB, I can differentiate this. F prime of x is equal to 2x minus 5. And f of A equals fb at one point. So what that's saying is, can we factor this? Let's find out. X times x. Let's see, 2 times 3 is 6. negative, negative, because the middle term is negative and the in term is positive, which means that we had to add two negative terms to get that, and then therefore multiply two negative terms to get this positive. So I'm going to say 2 and 3, because 2 times 3 is 6, and negative 2 minus 3 is negative 5. So at x equals 2 and x equals 3, f of x equals 0, f of x equals 0, and that's just multiplication. So what does that mean for us? That means that there is at least one number c in the open interval for which f prime of c equals 0. So, and the reason I did this a little bit is because we have to show that f of 2 equals f of 3, just in case anyone was curious. So now let's find out. F prime of x equals 2x minus 5. Let's set that equal to 0. 0 equals 2x minus 5 plus 5 on both sides plus 5. So then we get 5 equals 2x. Divide both sides by 2. So we get x equals 5 over 2. If you say 2.5, just go away. I don't like decimals. So 2.5 or 5 over 2, that is indeed between 2 and 3. But the inflection point is where the second derivative is equal to 0. In that case, it was 2, right? That is 100% correct. Yes, very good. Very, very good. Awesome job. SO, Alex Jones. Yeah, the inflection point is where f double prime of x is equal to 0. I will write that on the board because that is something worth knowing. Oh, snap. Oh, snap, y'all. I just found like 3 markers in my chair. That's pretty nice. Now I'm changing colors. So yeah, inflection point. F double prime of x equals 0. And then the inflection point is whatever the coordinate for x is. It's the c value. So yes, that is actually a very good question. Thank you for asking. Okay, so now what we're going to do is the mean value theorem. We've got, and I'm just going to read this one out loud because I think I went over this last time. So f is a function defined on the closed interval from a to b if f is continuous on the closed interval from a to b. Okay, sounds familiar. F is differentiable on the open interval a to b. Sounds very familiar. Then there is at least one number c in an open interval from a to b for which f prime of c is equal to f of b minus f of a over b minus a. So basically what we're saying is that, oh, this is real cool. The derivative of f of c is equal to the rate of change for a and b if it passes the conditions of the mean value theorem. So let's just run before we can walk. I mean, you know, let's just dive head first. If it's the shallow end, just catch yourself. If it's the deep end, hold your breath. So let's start with this example question right here. F of x equals x cubed minus 3x plus 5. Oh, snap. Okay, so now what we're going to do is let's see. I guess we can take the derivative. F prime of x is equal to 3x squared minus 3. Oh, snap, y'all. Oh, cool. Okay. I was looking at my notes and I was like, man, I must have done something real wrong there, but I just skipped a step and did it in my head, I guess. Don't follow my example. Always show your work, especially in your notes. Especially in your notes. Keeping good notes is essential to being good at this class. So this right here, you guys should recognize that. It's a difference of 2 squares. That's what they call it in schools now. You know, they used to just tell us it was a difference of squares when I went to school, but I'm tutoring like a rising 9th grader, and he said that their teachers, they call it a difference of 2 squares, and they make them call it dots. When they answer, like in class, they have to say dots. Like the teacher goes, what is this an example of? And instead of saying a difference of 2 squares, they just say dots. That bugged me a lot, but basically, we just FOIL it out like this. Oh, snap. That was pretty nice. So then we got x equals 1, x equals negative 1. That's looking like our a to b. It do be continuous there. It also do be differentiable. And oh snap, f of a do be equal to f of b. But that's Rolle's theorem, so that doesn't even matter. So you know what? This does pass Rolle's theorem as well. But the real question is, does it pass the mean value theorem? So we go f of 1 is equal to 27 minus 9. Oh, just kidding. 1 minus 3 plus 5, so negative 2 plus 5 is 3. And then f negative 1 is equal to negative 1 plus 3 is 2 plus 5 is 7. So what we're saying here is that there should be a number c that exists. So I'll rewrite this. We got 3 times some number c squared, which is just taking this right here, right? And bringing it down here, minus 3 is equal to f of b minus f of a over b minus a. So f of b is 3 minus f of a, 7 over 1 plus 1, as we're doing 1 minus negative 1. So then we're saying 3 times c squared minus 3 is equal to negative 4 divided by 2 equals negative 2. Add 3 on both sides. So we get 3c squared equals 1 divided by 3 on both sides. Take the square root on both sides, then we get c equals plus or minus the square root 1 over 3. Or if you really don't like having radicals like that, then you can rewrite it as this. C equals plus or minus the square root of 3 over 3. And that's just simplifying the radical out of the denominator. But that's how the mean value theorem works. You just see if one thing equals the slope of the other. You see if there's a connection. It's actually a really cool thing. Like, if you think about it, I mean, it almost seems like magic when you think about it, that there is at least one number c that is equal to the rate of change for the second derivative. For the second derivative at c is equal to the rate of change for b and a in the first derivative. Or first derivative and then the first function, not second and first derivatives. But that is a cool little trick because, I mean, it may not seem useful right now, but if you want to find like a point where the slope is going to be equal to the critical number, like you're trying to find critical numbers. So this is mean value theorem. Gosh, there's a really cool application for it. It's like, so the derivative of f of c equals the rate of change from A to B. Yeah, so I mean, this is kind of just the definition of the derivative, but you just happen to be finding it inside of a derivative without already knowing A and B. Yeah, there we go, there we go. We're using critical numbers, rules of continuity, and rules of differentiability and equivalency in terms of zeros. Oh snap! So this is like this is almost like the Maclaurin series for Calc 1 because it's all based around the concept of zero. So this seems pretty cool right now, guys. But if any of you are taking Calc 2, it's going to be like just like this, except it's not going to be applications of the integral. It's going to be your guys' favorite things, which of course is Riemann sums. Sorry. Excuse my southern word pronunciation. Riemann, that's his name. Okay. So yeah, that's the dealio with the mean value theorem, Rolle's value theorem, and critical numbers, and as well as test for concavity, critical points, second derivative test, the first derivative test. Shoot, I would say we are on schedule. So with that in mind, we are going to do some integration. Finally. I am very excited for this next chunk. I told you guys I was going to be hopping around, so I think I got all the stuff right there, right? Yeah. So let's just, I'm just going to assume I did until one of you asks me something. Oh, snap, L'Hopital's rule. Okay, I lied. There's one more thing we need to do before we get to integration, but this is kind of a cool concept too. So the theorem of L'Hopital's rule states that f and g are differentiable functions on an open interval I containing the number c except possibly at c. G prime of x does not equal 0 for all x does not equal c in I. L equals real numbers or plus or minus infinity. And f of x over g of x is indeterminate form as c of type 0 over 0. So I just read a bunch of nonsense that you probably didn't listen to. So now I'm going to actually write the cool thing right here. So I'm just going to kind of summarize here. So 0 over 0 if limit as x approaches c for f of x equals 0. And limit as x approaches c, g of x equals 0. And this is this is just pretty much telling you guys how you get it, because it's saying that that's all of that is the result of limit as x approaches c for f of x over g of x equals 0. So if x approaches c, there's another, this is one form of when you should use L'Hopital's rule. Another one would be if you get something like infinity over infinity, or 0 over infinity. No, not 0 over infinity, that's just 0. Let's see. So I think it's better if I just do instead of think. How about we do that? So let's just take a function. This is for limits approaching some number, by the way. So let's take, we got limit as x approaches infinity for x squared over e to the x, which is really just equal to limit as x approaches infinity for x squared over the limit as x approaches infinity for e to the x. So this is just going to obviously give us infinity over infinity. But, oh, don't worry, I like rules here. Good. Okay, so infinity over infinity, that's an ugly looking thing right there. I'm not a fan. We don't like that in calculus. So L'Hopital, this guy, he was like, oh snap, check this out, y'all. He went, you can just take the derivative of that until it works. That's pretty much what he said. So he said you can go like 2x. Oh man, that's not nice. Yeah, you take the derivative of the top and the bottom, so we go 2x over e to the x. Still going to be infinity over infinity. Then we go 2 over e to the x. And that should be 0. For x approaching infinity. Oh snap, look at that. I was right. Okay, so let's do this one. Let's do another one. And then we'll do some integrals and stuff. This is just a thing in case he asks you about it. Just differentiate top and bottom until it works, pretty much. That's pretty much all you have to do. Okay, so limit as x approaches 0 for tan of x divided by 6x. Okay, so what is tan of 0? Tan of 0 is equal to sine of 0 divided by cosine of 0. So let's think. Unit circle, right? It's a circle. So cosine is our x value, so 0. This is going to be 1, 0. So tan, when x is equal to 0, tan of 0 is equal to sine over cosine, 0 over 1, so it's equal to 0, divided by 0. Snap, that doesn't work. We need our good old pal L'Hopital. So let's derive. So now I'm just gonna change that to an arrow because they're not equivalent, or they are, but it's weird. You don't have to worry about it quite yet. And then secant squared of 0. So if cosine of 0 is 1, then 1 over 1, or 1 over 1 squared, my bad, because this is just 1 over cosine of 0 squared, just equals 1. So that means when x is approaching 0 for this, we get 1 over 6. And the reason this works is pretty simple. This theorem states that if the limit as x approaches c for f prime of x over g prime of x equals L, then limit as x approaches c for f of x over g of x also equals L. And that is because we are going down in degrees. Or at least that's my general gander on the matter, thinking just out loud and logically. There might be a mathematician that could give you a better explanation, but I'm pretty sure it's just because you're going down in degrees when you take a derivative every time. So of course, the next thing is going to be within the realm of the first thing because you're going down, not up. With an integral, it wouldn't work that way. Actually, it doesn't matter either way when you think of it. Okay, one optimization, just one. And then integrals. I'm saving integrals for the last because I want you guys to like really hurt your brains thinking about this stuff. And then your brain, through that pain, the math will just make you feel so empty that your brain will finally be able to absorb new math. At least that's what my research advisor told me last semester. Because you know what, guys? When you have to spend an entire year getting 120,000 points of data and also teaching math and taking 3 math classes at the same time per semester and computer science, you just kind of learn that no one really knows a lot, but everyone can know a lot. So, I don't know. I guess it makes you work harder because you know that anyone can work harder. Okay, so x, y. So we're given this formula right here. This is not fenced. And we're given p equals 2x plus y, and a equals x times y. And that's just because it's a rectangle, length times width. So let's see what they want us to do here. So 4,000 meters of fence. By the way, these problems always draw them every single time because you want to think about it, and you can't think about it if you don't draw it. Equals 2x minus y. Two x minus y. This is just algebra. Haha. Wait a minute, why is this negative right here? Oh, because I was going to take it away. And then we go y equals 4,000 minus 2x. And now we just plug it into this one. So now we get a equals x times 4,000. Don't worry. Oh. Did my laptop just glitch or something? No, we're good. 4,000 minus 2x. And now we have it in terms of x. Let's distribute that. We get a equals 4,000 x minus 2x squared. A prime equals 4,000 minus 4x. I'm sure you're all confused right now on what I'm doing, but I'm getting there. A prime equals 4 times 1,000 minus x. Oh, by the way, I never told you guys what the problem was because I didn't want you to know. So now I'm gonna keep not telling you what the problem is and then solve it. And then I'll let you know what's going on. So check this out, right? So 4,000 minus 4x. So critical number f prime of 1,000 is equal to 0, right? Critical number. So now let's take that critical number. And now we have x equals 1,000. We're going to get y equals 2,000. Yep. And that's the optimal way to fence in this area. With 4,000 meters of fence, it will cover the most area. So now I know I didn't really explain this, but hear me out. There's a reason I did that. Because I wanted you guys to just kind of watch for a second before I went into detail. So what we're saying here is that we've got a 4,000 meters of fence, and we want to box in this much land right here, but this front part here is not fenced in. So the parameter for the fencing total is P equals 2 times X plus Y. And then, of course, area is just going to be width times length. So what I did with this problem was I said, hey, I know exactly how much fencing I'm going to put on the parameter. It's 4,000 meters. So I went 4,000, therefore must be equal to 2x plus y. But that's not good enough for me. So then I went, well, I've got this other formula that I haven't used yet, a equals x times y. So why don't I just try and solve for y here so I can plug it in for y down here? And what that gave me was it gave me, 4,000 equals 2x plus y. I subtract the 2x from both sides, so I got y equals 4,000 minus 2x. I plugged in 4,000 minus 2x for our y variable right over here. And then what I did was I multiplied it out, differentiated it, and that gave me 4,000 minus 4x. I decided to find the critical number, because that is going to be our optimal area. And once I found the critical number for x, I just simply plugged it back into the original expression for the parameter to find out what I would be using for y. So essentially all of optimization is first, read the problem until you can identify a quantity, find out if it's a max or a minimum to be found, assign a variable, draw a picture, assign symbol to the other variables, find relationships between the variables like I did with the perimeter and the area. And basically you can do that through substitution. That's normally going to be the most efficient way to get around that. After that, you're going to want to express quantity that is to be the max or min as a function of other variables, like what we did right here. So we got it down to a singular variable, or well, not singular quite yet. That's what we did here. So we got it into that, so we can plug it in there. Then what you want to do is isolate the variable, which is what we did here, by getting it down to just x, by getting area into just terms of x. So then you plug it back in, use the first derivative, and once you have your critical number, you just simply go back to f of x, not the first derivative one, and then you just plug it back in for whatever you're looking to optimize. And that's a little crash course on optimization. Put the thing where it needs to go and do the math when it needs to be done. Don't make yourself work too hard. Any good integrals in here that you guys can learn yet? All right, well, you know what seems like a good closing note for today? Because everybody certainly wants to know, like, what this is. I mean, guys, like, the name of the course is in this theorem. I mean, if you're leaving the session now because it's an hour, like, you're missing out on the bee's knees of the session here. This is, like, what you've been waiting for. You know, like, when they say, like, the word B in the B movie, or when he says, I am Iron Man, like when they say the title of the movie during the film and you go, oh, snap, that's cool. Yeah, that's what's about to happen here, guys, because, oh, and you guys get a two-parter here. So this right here is the fundamental theorem of calculus. That's right. And there's two parts. Part one. All right, let's see if sophomore, freshman Nick, whenever this was, when I took Calc 1, had good handwriting. I did not. That's something else, guys. If you want to get really, really good at this class and math classes in general, just make your handwriting stupid good. Practice it all the time. Mine's not great, but it's a lot better than it used to be. And I put a lot of effort to get it there. I'm still working on some things like that, but you're not going to want to do it if it doesn't look good. People like aesthetic things. Alrighty. Okay, cool. So fundamental theorem of calculus part one, right? So if we take the derivative of the integral of f of x dx, and all this is saying is that this is equal to f of x. Oh, snap. Okay, ready for the next part? Part two, fundamental theorem of calculus. The definite integral from a to b for the function f of x dx is equivalent to the antiderivative f of b minus the antiderivative f of a. That's the fundamental theorem of calculus. So roll credits, you know, the big moment you guys have all been waiting for all semester for them to say calculus is here. And yeah, let's just do one. Let's do a definite integral. Why not? That sounds kind of fun. That sounds like a good time. Or something that's like, has this passed you guys yet? Yeah, that's not the move. Let's do. Let's do this one. Just an easy one to end the day with. -2 to 1 x squared dx equals. So we want to take the antiderivative. So we're going to raise the power +1, divide by +1 to the power from -2 to 1. So 1/3 plus 8/3 equals 3. That was a fun little cute one to do. All right, guys, I hope this was helpful in any way it could be. I know you all have a test coming up, so I did a lot of the very basic, big picture-esque ideas today with some examples just to kind of show you how it goes when you're working through it. I hope that this was helpful. I really want you all to be able to do well on this next test so you can have some, not be super stressed going into the final. But our next session will be held on Tuesday at 5 p.m. and then our final session will be probably Saturday before the final day. But it might have to be sooner. I'm gonna have to check with my boss. But yeah, so that's the deal for today. Thanks for coming, y'all, and have a good day.